So in this video, I am going to discuss about the Seyferth-Gilbert homologation, and you can see the reaction condition is basically you have a ketone and you are reacting this ketone with this dimethyl diazomethyl phosphonate in presence of strong base like potassium tert-butoxide in THF solvent and at minus 78 degrees centigrade. So at the very low temperature is used in this reaction, although at the later stage of the reaction mixture is slightly warmed up and you will get this alkyne. And this reaction, when I will write the mechanism of this reaction, it will remember you the mechanism of the Corey-Fuchs reaction as well as the Wittig reaction. But there is a modification of the Seyferth-Gilbert homologation condition, and this uses the Ohira-Bestmann reagent. Ohira-Bestmann reagent is same as used for the Seyferth-Gilbert homologation, but in this case, instead of this dimethyl diazomethyl phosphonate, they used the dimethyl 1-diazo-2-oxopropyl phosphonate. And by using this they can do the reaction with mild condition like this potassium carbonate base. They didn't need this strong tert-butoxide base. This reaction is less sensitive to the functional groups. For example, if you have such a aldehyde which can enolize and that is that can undergo aldol condensation at the Seyfert-Gilbert condition because it uses very strong base. This aldol condensation you can prevent by using this Ohira-Bestmann reagent. Now let us look at the mechanism of these two reactions. So first I will discuss the mechanism of the the actual Seyfert-Gilbert reaction, and for that we have this dimethyl diazomethyl phosphonate and we have tert-butoxide base. So first step, the tert-butoxide anion will deprotonate from here to give you this. Here you have a negative charge. Okay, now this deprotonated reagent is added to the reaction mixture, and there you have this, let's say you have this ketone R dash, you have this ketone. Now this negative charge will attack at the carbon, so it will basically form this. The next step is the same step as happened with the Wittig reaction. So this O minus will attack on the phosphorus, so this will first go, but then OMe can go. Okay, or this doesn't need that because phosphorus has phosphorus can attain highest coordination number of 5, so this can just open and you will be getting this. So here you have O minus, here you have OMe, here you have OMe, and here you have this R dashed R, and here you have this N2. Now the same reaction as happened for Wittig reaction. So this oxaphosphatane will collapse like this, and you will get this intermediate. Okay, so this intermediate you will get here. Now here you will have negative charge, here you will have positive charge. So you know, whenever you have this situation, nitrogen gas can go like this, and if in this step a nitrogen molecule removes, you will have this carbene, phenylidene carbene. Now any of this R group can migrate here, so that will basically give you, and this negative so here if this group migrates, you will have this. Here you will have a positive charge and here you will have R dashed. Okay, and here you will have a negative charge. Now this negative charge can go here and you can get this alkyne, or you can write down this step. This reaction is in a single step, that is when this R dash group is migrating here, you can draw a arrow like this to show this product in a single step. So this is how you will get the alkyne starting from a ketone and the Seyferth-Gilbert reagent. Now the similar reaction happens for the Ohira-Bestmann reagent. So the Ohira-Bestmann reagent is basically this one. So this is your methyl 1-diazo 2-oxopropyl phosphonate, and in this case it uses the mild base potassium carbonate and methanol. So in this condition methoxide will be generated, and that will attack at this carbonyl center to this reaction, and in this case in situ you will generate this. So now the rest of the reaction is similar. So this thing, the same thing you generated here, and the rest of the reaction follow the similar pathway, and you will get. So in this case previously we used ketone, but if you use aldehyde you will get this terminal alkyne. So this is a very good reaction, and the mechanism is very good. You can find similarity of this mechanism with the Wittig reaction and the Corey-Fuchs reaction. So I hope you enjoy the video. Thank you for watching.